two more article is actually left, article 8.9. So we are not actually going to go in detail of this article. This is actually with the positive feedback. So far whatever we have discussed is with the negative feedback system, how to plot the root locus. So in article 8.9, it is all about root locus for positive feedback system. So we'll just introduce the topic and give it as a self-study. So root locus because in real life, most of the system is actually having negative feedback. So it's just to know how to approach to the system, we are just introducing the topic. So root locus for positive feedback system. Feedback system. Okay, so block diagram wise, the change will be something like this. So whatever your kg of s, and then you have the feedback h of s. Only the difference is here you have a plus sign. Okay, so this is the difference. This is your plus always. Okay, so equation wise, what will be the difference? The equation wise, closed loop transfer function will be something like this. Ts equal to k g of s 1 minus k g of s h of s, which is nothing but your characteristic equation, this one. So now the characteristic equation is different. And based on the characteristic equation, basically we figure out the properties of the root locus. So characteristic equation. So our root locus will be something like this. Now new characteristic equation is 1 plus k, sorry, it has to be 1 minus k g of s h of s has to be equal to 0. That means k g of s h of s equal to 1. Okay, so as before, we present this one in polar coordinates. So the value has to be, magnitude has to be 1, and the angle has to be k times 360 degree. Okay, so basically this one we are talking about. Okay, so now as you can see, previously to figure out whether any pole is on the root locus or not, we actually were seeking odd multiple of 180 degrees. But in this case, we'll be looking for any multiple of 360 degree will give you the point on the root locus. Okay, so what are the rules, drawing rules that we have introduced are going to change. So let us figure out the rules, those. So we just make 2 columns, no changes, rules, no change. The rules that will not, will be remaining as it is, and changed once, So the first of all, actually, as you can see, the most of the thing will be remaining same, except the rules that are related to the angle that will be changed. Okay, so firstly, number of the sorry about it. Okay, so firstly, number of the branches, will it be changed? No. So number of the branches, the rule 1 will be remaining as it is, number of branches. Which one is higher? So that will be remaining as it is. Then symmetrical, because the complex pole will be appearing in complex conjugate. So symmetry will be also same. Okay, so number 3, real axis segment. So real axis segment will be changed. The rule 3, that real axis segment formula was left side of odd number of pole and 0. So it will be now left side of even number of poles and zeros. Okay, so odd number is related to odd multiplication of 180 degrees. So even number is related to whenever the number is even, it is always 360 degree that is coming. So that is why this is how they are related. But it has a complicated formula derived in the appendix. So if you are interested, I can cover that one as well. So let me know whether you are interested. This is complicated. That is why they left in the appendix. They just use the formula, but they haven't derived it. So if you just let me know if you are interested, then I can go in detail of that one. And next is your starting and the ending point. It is also remaining unchanged because it is related to the value of the k going to 0 and infinity. So starting ending points is remaining same. Starting and ending points. So that means from pole to 0, same as before. Okay, so what about the behavior at the infinity? Rule number, sorry, this is rule number 4. Rule number 5 is because it is related to the angle, so it will be changed. So real axis intercept, it will be remaining as it is because it is not related to the angle. So summation of the poles minus summation of the zeros divided by the number of the poles minus number of zeros. Okay, so but this is unchanged part of it. But what about your theta A, the asymptotic lines? Previously it was twice k plus 1 or multiple of, so it will be now replaced by k twice pi or 360 degrees divided by number of poles minus number of zeros. Okay, so these are the basic rules. The rest of them are also actually remaining unchanged. So the ones that are related to the angles will be changing only. And this time actually we are looking for any point to be on the root locus. It has to be any multiple of 360 degrees will be on the root locus. An example, one of the example that we have seen is for a closed loop transfer function like this, k s plus 3, then you have s plus 1, s plus 2, and s plus 4. Common one, we already used this one. So for this one, h of s, because h of s is 1. So how it will be looking like for your positive feedback. So if you want to look at that one, so let us just look at the book. We don't want to draw it because most of them will be similar. Only the angles will be changed. So what will be the angles? The angles will be twice pi let me just figure out the angles for you. So sigma A will be remaining unchanged. Sigma A will be minus 1, minus 2, minus 4, minus 3, divided by 4 minus 1, that is 3. Okay, so what will be minus 4 by 3? So the location, the centroid of the asymptote is not changing, minus 1.33. How the angle is going to change is basically k twice pi by 4 minus 1, that is 3. So k times twice pi by 3. So three infinite lines should be there. So if k equal to 0, then we are going to get 0. Okay, so these give us the theta a equal to 0, which is one of them. And then you have k equal to 1, then you have theta equal to twice pi by 3, twice pi by 3. That is actually 120 degrees. And k equal to 2 equal to theta equal to actually 4 pi by 3. That reflects to actually 240. So if you now look at these angles, previously it was 60 and 300. Now it will have 120 and 240. So just opposite. Okay, so now try to plot this one. If you try to plot this one, what you're going to get is, let me use the ruler. Okay, so if you try to plot it, okay, the ruler takes a bit of time, but it is actually helpful in the long run. So now just very briefly try to plot this root locus, even though we are not interested to go in detail. So poles that we have is this one, s equal to 0, s equal to 1, s equal to 2, and s equal to 4. Then we have 1, 0 here. Okay, now the segment, which one will be on the root locus? Is definitely odd, even numbers now. So this segment will be on root locus. Actually, this is consistent with our angle. So one of the angle is actually 0 degree. Okay, so next segment will not be on root locus. So this one will be on root locus. And then you have the next segment, this one will be on the root locus. So these are the three segments. So definitely this will go from this one to this one. And this one is going for this 0 at infinity, somewhere at infinity. And for this segment here, our centroid is 1.33, somewhere here. Okay, so and then if you try to plot 60-degree lines, then you're going to get 120-degree lines, so you're going to get something like this. Okay, so this will be your, from the centroid, this will be your lines. So identical lines will be downwards as well. Okay, so somewhere like this. Okay, so if you now plot, so we are not going in detail. That is why we are not actually figuring out what is our break away point. So, but we know that we'll have something like this. So they will be merging together to some point, and that point has to be somewhere here. So they'll be merging because we cannot cross the cross our asymptotic line. So they'll leave from this vertically from these 2 points. Then maybe gradually it will be one will be going towards this line, and the other one will be going towards this line. This may be the plot related to the positive feedback system. Is it okay? So this is your root locus, how to draw the root locus for positive feedback system. So, but we are not going to go in detail because in real life, most of the system actually goes with the negative feedback. So we focus more on that one. Now, last article of this chapter, this is I think 8.10. So that is pole sensitivity. 8.10, that is pole sensitivity. So pole sensitivity, what it says is how the pole is how much the pole is sensitive with the gain. So pole sensitivity. Okay. What does it mean is actually with changes in K, how much we have changes in your pole location. So this is all about pole sensitivity, and the formula is also simpler. In the chapter 7, we already derived sensitivity of any system. In this case, our system is a pole. With respect to the variation in the parameter, is parameter divided by the system, then rate of change of the system with respect to the parameter. Okay, so same formula we are going to use. We are not going to derive anything new. And somehow, if you want to know that for a change of del K, how much change we have in del S, then we can actually change this formula a bit. Instead of the derivative, we can also represent with a small change. So K by S del S by del K. So in that case, the formula we are interested about del S. So formula will be something like this: S times the sensitivity that we have measured, sensitivity of S in terms of K. With that, we have a change in K. So del K by K. So say 10% change in K means actually del K by K equal to 0.1. Okay, so let us look at one example. Example 8.10. So let us apply this thing. So example 8.10. So the basic problem that we started with, camera security system at the beginning of this chapter. Camera security system. So we had the characteristic equation something like this, a closed loop equation, K by S square plus 10S plus K. So this is our characteristic equation. So based on that, we can find out the derivative. So del by del K, S square plus 10S plus K. So this is equal to 0. So this is equal to 0. So now we have 2S. Then we have 2S del S by del K plus 10 del S by del K plus 1 equal to 0. So we can take common of it. So twice S plus 10 del S by del K equal to minus 1. So del S by del K equal to minus 1 divided by twice A plus 10. So now you have del S by del K. So our formula for sensitivity of the pole with respect to the K is K by S, then del S by del K. So you just put the value of del S by del K here. So minus 1 twice S plus 10. So one of the point of your table 8.1 was for K equal to 5, we actually figured out that S equal to minus 9.47 was one of our pole. So at this point, if we try to find out the sensitivity, then S tends to K equal to k by 5, k equal to 5, so 5 by minus 9.47 into minus 1 minus 2, sorry, 2 into minus 9.47 plus 10. Okay, so if you just use the calculator, then you're going to see that the value here comes as minus 0.059. Okay, then they're asking us, this is sensitivity. So at this point, this is how, for a small change in K, this is how the value of our pole location will be changing, and correspondingly, because the pole location is related to the system behavior or performance, so correspondingly our system behavior also will be changing. So now they're saying that for 10% change in gain, or what will be the change in the pole location for this particular case. So 10% change, 10% change in gain. So basically what they have given is del k by k equal to 0.1. So let us find del S equal to S, the pole, times the sensitivity, S tends to K, S to K, then you have del K by K. So pole location is minus 9.47 into minus, sensitivity is minus 0.59, then you have 0.1. Okay, so what you're going to get is 0.056. So what does it mean? For 10% change in gain, we are going to have a 0.05 unit change in your pole location. Okay, so this is relatively simpler if the things are in, because all of them are in the real number, but you can also apply the formula for imaginary number as well. So say another point for k equal to 50, actually our pole location, one of the pole location is minus 5 plus j5. So in this case, what is our sensitivity and how we are going to find out for 10% change. So first question is sensitivity of S tends to S to K, and what is the value of it, and for del K by K equal to 0.1, what is the value of your del S? So this is what they want to know. Okay, so let us start with the sensitivity first. As tends to K. Okay, so is K by S. Then you have the formula that you have derived, previously minus 1 twice S plus 10. So now if you put the values here, so 50, then you have minus 5 plus J5. Then you have minus 1, 2 into minus 5 plus J5 plus 10. So minus 50. Then you have minus 5 plus J5. Then you have, so if you multiply, then it will be minus 10, then plus J10 and plus 10. So 10 will be getting cancelled out. What will be left with is only J10. So if you just multiply this, then what we are going to get is minus 50, then you have minus 50 J plus J square 50. Okay, so minus 50, J square is minus 1, so you can take the minus common, so what will be left is 50 plus J 50. So this thing becoming plus, Now you can take the common of the 50. So 50 can be cancelled out, 1 by 1 plus j, which can be represented as magnitude in terms of magnitude and angle. What you can find is 1 by root 2 magnitude, and angle is 45, or if you take the angle to the numerator, then you have 1 by root 2 minus 45. Okay, so this is sensitivity, complex number of sensitivity, what do you get? Okay, so now the next portion, for 10% change in K, what will be the value of del S? So let us try to figure out. The del S is S times the sensitivity, S, sensitivity of S for K. Then you have del K by K. The point is minus 5 plus J5. Then your sensitivity is, you can say, whatever formula you want to use, you can use. Then you have into 0.1. Okay, so 10% change. So now if you take common of your 5, then what you can find, actually, if you write in terms of magnitude angle, then it will be easier to calculate. So magnitude will be root over 5 square plus root over 5 square, root over 5 square plus 5 square. So basically 5 root 2, and the angle will be tan inverse minus 1, that is minus 45 degrees. And we already calculated for this one in the polar coordinates, 1 by root 2 minus 45 degrees. So into 0.1. So basically root 2 getting cancelled out. So minus 45 minus 45 is becoming minus 9. So also you can multiply this one with this one. So it will be 0.5 minus 90 degrees. So minus 90 degrees is nothing but actually minus j. So minus j 0.5. So what does it mean for 10% change in K? Actually, vertically, since you have J, vertically the pole location will be changed with a factor of 0.5, which is true because of the fact that we have seen that our root locus was actually going up and down. Okay, at minus 0.5, one started going up, the other one started going down. So only the vertical distance will be changed. So this value, real axis value, is not changing. Okay, so this is how you have to find out the pole sensitivity, and for certain change in K gain, how can we actually find out what will be the location of your pole? Now, this is the end of chapter 8. So we can start the chapter 9, or we can also look at a bit of that example that we are saying. So example 8.8. So in the example 8.8, example 8.8, I will give you the handout because of the fact that I'm going through a bit of busy time, so I can finish it. But don't worry, I will give you the handout of this one. So they have given a system like this. And now difficulty with this particular case is K S plus 1.5, and then S plus 1, and S plus 10. So unity feedback, negative feedback, so everything is okay. Now, by looking at this equation, Kg of S, H of S, so what does it seems, how the root locus should look like? K G of s, h of s is ks plus 1.5, s plus 1, and s plus 10. Okay, so let us do a bit of experiment on this one. Before going to the experiment, so let us try to predict the root locus. So try to predict the root locus. Now, according to our prediction, how it should look like. Okay, so according to our prediction, we have one pole at origin. So we have one pole at origin. We have one pole at 1, minus 1. Then minus 2, 3, 4, 5, 6, 7. So 1 should be somewhere here. Okay, and 1, 0 at 1.5 here. So tell me how the root locus should look like. So definitely a number of the branches has to be number of branches has to be 3 because 3 number of pole we have. Number of infinite line should be number of infinite lines should be 3 minus 1, so 2. And the angle should be twice k plus 1, 3 minus 1 into pi. So basically pi by 2 into twice k plus 1. So if k equal to 0, then angle should be 90 degree. And if k equal to 1, then angle should be 3 pi by, so basically 270 degree. So this is what we assumed. And now what it looks like, we can have a simple curve like this. And I think they will be merging together and then up and down, isn't it? So far, whatever the knowledge of root locus we had, this is how it should look like. But is it reality? Let us go to the math lab and let's check how much we are going to deviate. So before going to that, let us find out the polynomial here. So polynomial will be, denominator will be actually s squared plus 11s plus s times s squared plus 11s plus 10. So divided by ks plus 1.5. So basically s cube plus 11 s squared plus 10. And numerator is ks 1.5. So let us look at how much it is going to vary from our prediction. Our prediction is the pole from minus 10, it will be going to 0 at minus 1.5. And there should be vertical lines going in between, somewhere in between 0 and 1 pole. Okay, so our numerator is 1.5, and the denominator is 1, 11, 10, and 0. Our system is going to be like transfer function num_den. You can use the convolution as well. I just prefer to multiply and then just finding the numerator, denominator. So convolution can also give you the polynomial. So now this is our equation. Now if you plot the root locus of the system, R locus R locus SYS. Okay, it's trying to plot now. Okay, so I have to go to that image window, the figure. Okay, so look at this one. So, is it any way closer to our imagination? Definitely not. So, as you can see, one is going vertically up and the other one is going vertically down, no question about it. But they are actually not starting from in between those two poles. Rather, uh, so we predicted that they will be starting in between these two and going up and down. But this is not what is happening. So rather they're merging to a break away point. So then they're going to a break in point. Then they have another breakaway point here. Okay, so this one is coming from this one and this one is coming from here. So as you can see in the MATLAB, it is very easy to figure out what is happening, which one is actually going up and down because they are showing directly. So it is far away from what we anticipated. And why this is happening, I try to investigate with that one. And the result for this thing is the location of the pole. The rest of the system doesn't make any difference. The value of the pole, the value of the zero is actually contributing to this one. So I have written one small program, script file, small, very small, and I have varied the values of your zero location, and based on that I try to plot the, okay, so now here script okay, let me open the script. So this is the script. So the value of the k is been changed. I'm just changing the location of the zero. Okay, and I'm changing it from 1.6 to 1.7. So in one of if the value of actually changing the location of the zero, then for some value in between 1.6 to 1.65, for some value the transfer is happening. So now let me draw it. Okay, so now look back again, the figure. Okay, so look at here, two of the value actually 1.6, 1.6 only actually merging here. 1.6 is for the location 1.6. Actually, it is merging here, coming, okay. And for the rest of them, 1.65 and 1.67, they are actually going in this way directly. So they're not merging into that axis. And okay, so the location of the zero is actually responsible for having a behavior like that. So that is why, even though I have said that in the book, they have said that article 3. Article 8.5 is basically 8.5 refining the sketch, but it is actually necessary, not essentially the refining the sketch. So it is also essential cases like this, where you can actually find out 3 sigma value, sigma 1, sigma 2, sigma 3, okay, and also the real axis breakaway breaking points, 3 sigma values you can find out, and then you can see that one of them point is here, so from and another point is here, so they're actually going this way. Okay, and another breakaway point you're going to find somewhere here. So one of them is going in that direction, the other one is going in that direction. So they're coming, and then you have that line that going up and down. And also you can find out that your reference line, so centroid, as well as your guiding lines, theta. So you'll find that they eventually have a path like this. Okay, so it depends on the rest of the refining the sketch that is actually giving you how to figure out the appropriate location. So far, this is the end of chapter 8.